So now that we have this work energy theorem, we can move forward from that. So consider this for a second. Imagine that we have a ball, and that ball is originally at rest on the ground. So we have ground, we have a ball on the ground. Now, at this point, the ball has zero kinetic energy because it has zero velocity. And as such, this ball really has no ability to do stuff, right? This ball can't push on anything and make it move as a result of its energy, right? So this ball is incapable of doing any work. So this is really like a no practical energy ball. But then imagine that we lift this ball up in the air so that it is moving. So I do positive work on the ball by lifting it. So now I exert an upward force on the ball, the force of the lift, and that upward force is going to cause some sort of vertical displacement as well. So now the ball is up in the air and it's moving. So now, I'm still in the little. Now the ball has kinetic energy and can do stuff. Yay. Yo. So now the ball can do stuff. But what if I stop lifting the ball and the ball stops? So now, in this last example, the ball is up here above the ground. It's up here, but it's not moving. In this case, Ke again, 1/2 mv squared is still 0 because no velocity. But doesn't this ball still have the ability to do stuff? Like, for example, this ball could fall, can do stuff, like fall. Right? And so if this ball can fall, then it must have energy. Much have energy. Oh my gosh. Oh my gosh. I'm losing my mind, people. Must have energy. This energy is stored. In other words, it's not doing stuff now, but it could do stuff if it was allowed to, right? So this is what we call potential energy. And potential energy is really, it can be defined as stored energy that an object has because of its position. In this case, because the ball is up off the ground, it has some height, and that height gives it the ability to do stuff like fall, right? A ball that is on the ground, like in this original case, no height, this ball cannot do stuff like fall. It's already on the ground, right? So the position of the ball gives it this energy. And there are many, many, many different types of stored or potential energy, but we will discuss a few of them. We will discuss gravitational potential energy. And this is usually denoted with a U sub G or GPE. The AP tends to use the U symbol. I tend to use the GPE symbol, but that's mostly because I teach a lot of lower level physics classes as well. But that's one type of energy. This is based on vertical height. So in this case of a bowling ball that's been lifted up off the ground, it has gravitational potential energy because it has a non-zero vertical height. We also have other types of stored energy. The other big one that we'll be talking about is spring or elastic potential energy. And spring or elastic potential energy is denoted with a U sub S or a U sub E, usually U sub S because E could also symbolize electrical, or SPE. And I tend to use the SPE, but AP tends to use US. And this is based on the stretch or compression position of a spring or elastic object. In other words, how much it's been stretched away from its resting position. So if a spring is normally 5 centimeters and I pull on both ends and it stretches to 10 centimeters, that would be a change in position of the spring of 5 centimeters. And that would store energy in the spring. In other words, a stretched spring can do stuff that a non-stretched spring cannot do. Therefore, it must have some additional energy. So let's look at this in a more calculable or quantifiable context, right? So gravitational potential energy. This is energy that an object has because of its height. So basically, if we go back to our bowling ball example, we could say, like bowling ball on the ground, no GPE, no U sub G, no gravitational energy. Bowling ball up above the ground, yes, GPE. So how did we get the bowling ball there in the first place, right? Well, in order to get it there, we had to apply a force on it, and that force had to cause the ball to change its position. And holy crap, that's work. Work is what gave this ball its gravitational energy. So work is accountable for the change in energy of the object. And that's what work really is, right? Work is a transfer of energy. Now, in this case, what was the force and what was the displacement? Well, if you imagine lifting an object, in order to lift it, my lifting force would have to be at least equal to mg, the weight of the object, right? These two forces would have to be at minimum equal. Now, you may be thinking, well, the lift force has to be greater in order to lift the object, and that's technically true to start the object moving, right? To get it going initially, but once it starts moving up, the lifting force only needs to be equal to the gravitational force in order for it to continue moving up. Furthermore, how much bigger would a lift need to be to get it to move up in the first place? It would have to be just barely larger than mg. So to get it moving, it would be mg plus 0.00000000000000000 infinite number of zeros, 1 newtons of additional force, which is effectively the same as mg. So the force of the lift, we can say, is equal to m times g. And in this case, the displacement of the lift, the amount of displacement that we're lifting this ball with, is equal to whatever the height of the ball is. So then the work done is equal to F times delta X, which is equal to mg times h, which is to say that the gravitational energy of an object that is at some non-zero height is equal to its mass times g times h. In other words, the energy gained by the object, and therefore the energy that is stored in it, is equal to mgh. So that's my formula for GPE, what it is, and where it comes from. Springs are a little bit more complicated. For springs, U sub S, or spring potential energy, spring force, we have to talk about separately. So in order to do the spring potential energy, we would need to know work done by a spring would equal a force of a spring times the displacement caused by the spring, right? Well, how does the force of a spring work? So spring force follows something called Hooke's law. And it says that the force of a spring is equal to negative k times x, where k is what we call the spring constant. It's basically a physical property of the spring, that is how stiff the spring is. So it's like a stiffness constant. Really tough springs that are really hard to stretch have very large k values, or coefficients, or spring constants. Springs that are very easy to stretch, or very loose springs, have very small spring constants and therefore exert less force. So that's what we call spring constant, k. And then x is the displacement of the spring from resting position. So, for example, if my spring was normally unstretched, like 2 centimeters unstretched, and then I stretched it to 4 centimeters, then x would be 2 centimeters in this case, how much I stretched it from its resting length. It's also worth noting that spring constant k is measured in newtons per meter, right? Because it's going to have to be, when multiplied by a displacement, it's going to have to equal a force. So you'd have k, newtons per meter, times x, meters, equals force, newtons. So that's how spring force works. It's called Hooke's law. Force of a spring is negative kx, and that's given in your data booklet. So then energy of a spring potential energy, the work done is the force of the spring times the displacement of the spring. But we have a problem here, because force of spring is equal to negative kx, where x is the displacement of the spring. In other words, spring force is a non-constant force. Non-constant force. So I can't just plug in negative kx for force spring and x for spring. I can't do this. Work equals negative kx times x equals negative kx squared, because this negative kx is non-constant. So this is illegal, breaks the calculus rules. Instead, I have to represent my work of a spring as the integral of f with respect to x. So that would be the work done by a spring is equal to the integral of negative kx dx, where k is a constant. So that is negative k integral of x dx, which is 1/2 kx squared. And that's negative, meaning that it just applies back towards the equilibrium position. As far as the energy that's stored, energy is a scalar quantity, and so it can't be negative. So in this case, spring energy is found to be 1/2 times the stiffness constant of the spring times the displacement of the spring squared. That is our spring potential energy.